Are we waiting on one more?
No, go ahead. I'll
Okay.
have to track down after Dr. Saki. It's another time.
Okay. Ma'am, gentlemen, this is GVR-Bot's critical design review. We are GVR-Bot. Group members are Cadet Pan, Cadet Bansky, Cadet Vosberg, who is at an honor board today, Cadet Moffitt, and Cadet Yurihara. Our GVR-Bot advisors are Major Larkin is our instructor, and Colonel Lawrence is our advisor. So our problem statement for GVR-Bot. We will develop a model for estimating the current battery state of the GVR-Bot and leverage this information as well as known discharge characteristics to accurately predict its future battery state for a known mobility path. Some of the assumptions we are making is that the GVR-Bot battery, the BB2590, has a discharge rate in a known, predictable way, so that each time we iterate through different batteries, all the batteries will discharge very similar to each other, so that our model doesn't have fluctuation between batteries. The route that we will be planning will be known and quantifiable. So for most of the route, we can determine what it'll be traveling on as per terrain or weather will be. And the test platform that we are using does not alter significantly the battery consumption.
Well, but I mean, the compared to what it would be without the test platform, is what you're saying?
Yes, yes.
Okay.
The addition of the test platform isn't drawing too much power from the battery.
Okay,
This assumption
gotcha.
was actually validated later, we'll talk about.
Gotcha, okay, all right, got it.
To try and reduce possible errors.
Yep, all right.
So our requirements are that we're able to accept a changing environmental input, which for this project we're going to hard code in. Eventually, the plan is to have it so that the robot can do this itself. Generally, we're expecting that to be accomplished with the Aribo platform. And the things that we need to model there are the physical and electrical load, the speed, and the temperature that the robot's operating at. It's accessible through a simple interface, which we'll talk about later. We have a UI set up right now. And then measurement techniques need to be simple and robust, which the current system that we have is our best iteration of that. And then database is going to include discrete voltage, discrete current, state of charge, time to empty, which is going to be an estimate based on the battery itself and the current discharge, and then the rate of discharge as well. Our constraints is that we're limited to the iRobot PackBot 510. The batteries of BB2590, and the specifications of that battery are listed up there as well. The robot is communicated with through Wi-Fi connection to the Ross laptop there, and our reading system is limited right now to 64 hertz from the battery and 84 hertz per channel from the data acquisition unit that we're using.
So product backlog.
Actually, just to clarify, so that's not 84 hertz per channel, it's 84 hertz aggregate?
It is per channel.
Oh, per channel, okay, so it's a 320 hertz.
Right. The
Gotcha,
theoretical
okay.
maximum for the system
Right.
is 10 kilohertz, but we've only been able to get it to 84 hertz so far
Okay,
per channel.
got it. But if your SM bus reading is only 64 hertz, then an 84 hertz
Right.
sampling is fine. Right.
So moving on briefly to our trailer product backlog. This is an example of our backlog no burn, and then next slide is our example of our backlog that was, I think, yesterday, before we inputted the hours for today. As you can see, we have a backlog. I think we have planned for the sprint.
This isn't a sprint review, keep going.
Okay, next slide, please.
So this is the updated block diagram from the last review. The only thing that's changed so far is instead of having an external battery as we planned, we changed the power supply unit you can see here to a buck boost converter, which allows us to pull electricity straight from the battery as opposed to adding on a separate power supply.
Okay. And what's a PSU?
Power supply unit. The one, there's two of them. One is for the robot itself, it's internal, and the other one is the one that we have connected to our buck boost converter. And that's
Okay.
converting down to 5 volts for the Raspberry Pi.
And the diamond with the vertical line through it that is in the center is represented?
That's the PCB. I'm not sure why the words aren't showing up.
Okay.
That's something that we fabricated ourselves.
Okay. Got it. Okay. It would be useful to indicate, so your DAC has 2 channels measuring
Currently, the DAC
voltage.
the DAC is set up to measure one cell of the battery,
Okay.
measuring voltage and current. Both of them are technically voltage inputs, and then we're converting the value to current.
Okay. And so yeah, what that PCB in the middle is doing would be kind of useful to break out. So you have 2 batteries, and you have 2 lines going to your DAC, but they're not for 2 different, they're not each battery, they're just one battery? The 2 red line, the 2 thick red lines going to the DAC.
All the PCB in the middle is
Mhm.
doing is taking the input from the battery here and moving it to the different outputs. One is, the top one is to the power supply of the robot, and the bottom 2 are to the DAC, so they can read.
What's going on there?
Okay, so those are the 2 different, the 2 12-volt cells. Okay. All right. And you've got a purple line, you've got an I2 signal.
That's a sensor signal.
That's coming straight from the battery now.
There's,
Yeah.
the color difference is kind of small.
Well, the temperature is purple, but you've got current voltage, state of charge, and temperature coming from battery 2. And
That's
then
SM bus.
through the SM bus. And how is that getting, it's going to an SM bus database, so you've got a computer that's physically measuring that?
This block here, ma'am, is the Raspberry Pi, and then
Okay.
each of these are databases within the Raspberry Pi.
Okay, so those are just within the Raspberry Pi, all right. And the DAC is pulling RPM and temperature.
We
Okay.
don't have it set up to pull RPM yet, ma'am, but that's an
But
option.
you
we're
will
looking
be.
at too.
Okay. For your bottom database.
Right, yes, ma'am.
Okay. So really the only thing the DAC is doing right now is measuring temperature?
It's measuring voltage right now.
Voltage and current.
Yeah, okay, it's measuring the voltage. How is it measuring current?
So what's going on then is battery 2 runs through the DAC and then into the robot.
Yeah,
And then the DAC is connected, if you see on here. So power is coming in to right here, and then we have a shunt resistor across
Okay.
the terminal. And then this is how we're measuring the current, because the current could spike to 20 amps, and we don't want to fry with that. So we're
Gotcha.
measuring the voltage across this resistor.
a circuit diagram of what that power, that PCB is doing would be far better. Okay, so that's how you're measuring the
Mhm.
current. All right,
And then
That
they just feed to the DAC.
okay,
This is one cell, and that's another cell of the battery.
okay,
The 2 channels.
yeah. All right, I now understand, but, yeah, the diamond in the middle doesn't really help you. Okay,
We can clean that up.
you
We will
will
clean that up.
need to, that little black box in the middle. Where's your block diagram?
It's not in there, ma'am, because we couldn't print in color, so it was,
Oh.
it's
We
printed
have
out. Is
we've
it
got-
it's in color?
We've got color printers in the study room that
I
are
think we
in color.
found it eventually.
Yeah, we do a full-size copy.
Right, okay, all right. Keep going.
Here is our delivery of product. So we have two GVR-Bots as of right now in the lab, ma'am. We have one in storage. We have two PCBs, two Raspberry Pi 3s, DIOP bonding plates, as you can see here, and 3 data acquisition units.
Okay.
So components and subsystems of our project right now. Hardware, we have the book computer, the DAC PCB Raspberry Pi. Software hardware is a Fidget Spatial, the data collection system. And purely software is the DAC parser, GVR-Bot source code, the image command UI, and the SMS parser. We're gonna go through all of these in much further detail.
All right.
We chose the buck converter because it allows us to step down the voltage from the 30 volts that the robot uses down to the 5 volts that Pi uses. There's a test plan listed
Yeah.
here that shows the voltages output across a wide range of inputs. It held it at a consistent voltage of at about 5.1, which is well within the specification for the Pi.
Yeah.
The DATAC, the acquisition unit that we're using.
So the nomenclature would be useful to, because you didn't design this buck converter yourself, did you?
No, ma'am.
Okay, yeah. So list the nomenclature, just because in future iterations of projects, somebody else might want to use it as well.
Okay.
Okay.
The DATAC that we're using, the test plans are going to be on the following pages, but the requirements that we had for it were that it needs to be measured at least out to 3 decimal places so that we were able to do the current and voltage measurements as accurately as possible. And we needed that to be at least accurate to 30 volts so that we could measure all of the voltages that we found on the robot so far. And it needs to accurately measure at the 2.5 approximate that we have at a minimum. The results that we had were that it's pretty accurate. We have actual numbers on this slide here. So test 1 is using the lowest gain setting, which was the 0 to 50 volt option.
Mm-hmm.
And that's the one that for a 30 volt measurement
Right.
we're going to be using. We had an average error of about 0.1 from the input source, and compared with the DMM, it's a little bit higher than that.
Which
And
DMM did you use?
we used the Agilent 6-digit that's in the labs.
Yeah, so again, when you brief these things, brief which pieces of equipment you use by nomenclature, because the accuracy of the DMM comes into play here when you're comparing one to the other. If your implicit assumption is that the DMM is more accurate, but that certainly depends on which DMM you're using.
Right. Yes, ma'am.
So, okay.
Our other test that we have is at the highest resolution, which is 0 to 2.5 volts, which is the setting we're going to be using for measuring the voltage across the shunt resistor. And for that, we had technically an average error of about 2 off of the current or the voltage source that we were using, but that also includes at the beginning there was there were 3 measurements that had error that was unusually large. So if you look later on, it goes down to less than 0.1 off of the actual. And then as compared with the DMM, again, we had about 1.2% error. This is an example using the oscilloscope comparison, which is on the right, and the DATAC software, which is on the left. As you can see, it captures the input frequency sweep with a pretty close accuracy. Next slide.
The next hardware component that we're with us is the PCB. The requirements was that the PCB could isolate the power coming from the battery from the SM bus data, as well as still enable the robot to operate fully functional without significant decreased performance. The PCB that we have fabricated has met the required specifications for operation on the GVR-Bot. It inputs both the voltage and the current, and then and the SM bus data, and outputs to the DATEC, which goes to the
Did you design this PCB?
Yes, it
Okay, so the design document, the multi-board or whatever needs to be in your documentation
Okay.
as well.
we will add that.
And again, that would be, the description of the PCB in words is useful, but the diagram, the circuit diagram, and then the PCB layout are what really are of engineering interest.
Okay.
Yeah.
We'll add that. And it runs as we need it to run.
For the Raspberry Pi, we use it to parse the necessary data, and we use it as basically a middleman between the database and where we're getting the data from. Requirements, it has met all the requirements to run both Python scripts simultaneously, have a small power footprint,
Yeah.
and
keep going. Got it.
So we, software hardware component, we had talked about a fidget spatial, and this is what Zach Bosford worked on mostly. He worked on a test plan that he assessed the accuracy of this.
Okay, so back up and tell me what a fidget spatial is.
So fidget spatial was a small piece of hardware that would use code and would help us determine the orientation of the robot based on its direction, like north, south, east, west, to a very specific degree. We're going to use this for the robots. So, for example, when we turn 90 degrees.
In how many axes?
It's a 9 degrees
Yeah.
of freedom now. It's got a gyroscope, a compass, and an accelerometer. So we're able to measure able to measure absolute position and also relative position with the original starting point.
Okay.
And our test plan was, Zach Vosberg it was 3 complete tests with 12 trials each, where he assessed the accuracy of just the direction of the fidget. And overall, the 3 tests, there's an average error of 19.6 degrees after recalibrating it twice for each test. So as of right now, this is one of our components that's not working. So next slide,
Yeah.
please. So this is his test for just an example of the error he's getting, and over time it wasn't consistent at all.
Was the motor running?
It was working sometimes, and sometimes it wasn't, and then over time it was anywhere between 30 degrees error and exactly on point. So we don't exactly know why. We've had it for a very limited amount of time, only about a week or so.
Tell me why. You know why.
This was actually off the robot. One of the concerns that we did have was that the robots have large permanent magnets and a varying electromagnetic field. But something that we've also found through other labs was that the hallways down here and a lot of the rooms have a lot of electromagnetic interference to begin with. And so you start getting some erroneous readings because there's a lot of that going on. This particular test was used on the desk without the robot nearby.
Okay, so for the data collection system now, we use a MySQL database, and then for the test plan, we would run the both parser scripts, and it would insert it into the MySQL database. And for the test results, all of it accurately inputted all the data from both the DATEC and the SM bus.
The GVR source code, so far the test plan we've conducted is an activity test, make sure the GVR-Bot works. Movement test, make sure all the different movement features of the GVR-Bot is functioning correctly. and then test could use controllers like the Xbox controller, command line controller, and GUI controller. So far all three of these tests have been conducted and all of them have passed. Next slide, please. This is a brief video of us just conducting one of the tests for the GVR-Bot. You want to play it? So all we did for this was we ran the robot initially and did functions like turn right, turn left, moving the flippers back and forth, just to briefly understand how the control's working and then maps its accuracy over time. So we've done this for both the robots we're working with right now, and this is assessing the functionality of the code behind the robot.
So, so this is code that you wrote to move the robot?
No, ma'am. So this is the
Right.
code we were given from I think it's Tardeck itself.
Right.
We've edited very little of it. We took their code and made it like version 1. We've added very small tweaks to make it work on our laptops to run it
Right.
automatically. But besides that, we've done anything.
So,
besides
so the
that.
code you were given works is what this shows?
Right. Yes,
Right.
It worked
Alright.
with the first one. This one we had to edit a little bit because the platform's a little different, but video's not really necessary. Next slide.
The next subsystem we have is the data parser. So basically we tested it by initializing the Python code that I revised from the.
Where'd you get this Python code from?
We got it from where did we get it from? We got it from the DTAC website, ma'am. It's basically a
Okay.
driver
Right.
to collect data readings from the voltages. I just revised it so it works in conjunction with the MySQL database and to get to collect data from the different channels. Also, it both work perfectly. Next slide. This would be the parser demo. Yeah, so it's on.
All of these videos are on the YouTube page we have,
Okay.
since they're not, they're gone now.
It's I use an offsite computer and I Wi-Fi'd into the Raspberry Pi, and from there I could initialize the parser for mobile testing. I inputted a print statement so you can actually see what kind of data we're actually receiving from the data.
Oh. And when you tested to see that you could only get 84 hertz, were you testing that by printing to the screen?
That was one thing that we did think about, ma'am, and then
Right.
we were doing it so we could print it.
Right.
We haven't revised it to try to go faster, but as we said before, our
Before then,
SMS is only.
I received it. I received the code for only putting out 2 hertz, but I increased it up to 88 hertz. So that's how much we're getting so far with this test.
But the very act of writing to the screen is slowing it down. Is what
Yes,
you're saying.
right.
Right, so if you needed it to go faster, you just don't write it to the screen.
So software subsystem, this is one of the major components of what we're doing right now. This is what we call the Mission Commander UI. And what it does is allows any user to walk up to one of our laptops and command the robot from a very easy to use, simple GUI. In our test plan for this, we did tests for movement control and tests for logging data. So far, both of these have not been completed because the UI is not done yet. For the model view controller aspect, the model and view is done. The controller is not linked yet to that process. So the next slide, please. This shows kind of our very brief model of how it works. There's a lot of different programs working together in unison. So on the screen itself, if this is still on, we have a small executable program,
Mm-hmm.
which you can click on, which will launch one of our bash files.
Right.
Once it's run in the terminal, which is done automatically,
Mhm.
it'll run our model, which uses our controller to launch a GUI that works for the robot. And as of right now, what it can do is it connects to the robot automatically, and it makes an easy-to-use controller for anyone to really use. This is a very simple joystick that someone can just go forward, back, left, right, and stop, which displays battery information. We also have pre-planned routes for square routes, linear routes, and actual mission and desk testing. And the point of this is to allow to us for desk testing or anyone in the future to do a mission and eventually have it display the battery percentage, have it displayed likely to complete the mission with the battery, make sure it doesn't die, and also like display current voltage and other information like that. So next slide, please. This is just a video of making sure it works, but we can show you in person, so next slide.
Okay, yeah.
The next subsystem we have is the SMBus parser. It works almost identical to the DATAC parser. However, it
Where'd you get that one from?
This one, ma'am, I made it by myself.
Okay, got it. All right.
As of right now, we have version 1.3, and it pulls the same way as the DATAC parser. But instead of just voltage, it pulls everything from the SMBus. It's basically the same way.
So subsystems that have not met requirements that we presented. First of all, Mission Commander, we are version 1.0.0 because it actually compiles no errors right now. The model and view are complete, and the controller is complete on its own. Both have been tested individually, but they're not linked together yet. So as of right now, the missing aspect is the ROS code compatibility between the two. So the next version is going to include a connection between these two that actually allows us to control it from the computer. Also, the fidget spatial, like we described, is not PRR requirements because of the inconsistency in tests. So next slide,
I mean,
please.
that's a huge jump from having an onboard accelerometer, so to go to using GNSS or GPS. I mean, what do you lose in doing that?
A lot of accuracy.
The XSense GNSS system, ma'am, also has an IMU. So we're able to put all of it together. It's just a higher end version of the fidget that we hope would help us get rid of some of the noise.
What gives you an indication that the GNSS is, the IMU within it is not going to be plagued by the same problems that?
We haven't been able to connect it yet, ma'am, so we don't know for sure.
Because with GPS, you lose all indoor capability, and you also lose any sense of the orientation of the robot and what sort of incline it's actually,
Right.
which will, I think, matter a whole lot in terms of.
Our understanding of the XSense is it uses a MEMS system, so it also has the same 9 degrees of readings in addition to the GPS. As we said, we haven't actually connected to it yet, so we can't verify.
Yeah.
Continuity for all the different code we're using and written ourselves. First and foremost, it's on GitHub using our version control, and we very detailed readmes for each file individually. Secondly, we have a 500 gigabyte hard drive that is located in our lab room. This also contains the same versions on GitHub, along with backup images for all of our computers, usually on a weekly basis. We have a Gemini file that holds all the code as well, along with our white papers that are found in our publication folder. And lastly, all of our code is printed out if everything were to crash at the same time in hard copy in our folder. Next slide, please. So for a code review, this is a lot of information. We're going to break it down, but this is a general overview of all the different codes we've done and who's responsible for it. We'll break that down in smaller pieces as we go on. Next slide, please. So for the GVR-Bot ROS code, like the thing that controls the robot itself, we are at version 2.0.2. This is stored in all the places we talked about before. And this is who's responsible, so it's mostly me and Zach Vosberg flipping off who's in charge and consulting Tam when needed and our instructors if we ever need to. Next slide, please. So we tested it. It has no errors right now. It compiles. Everything we want to works. The only error we do have...
So, time it. So it compiled without errors, or it compiles and actually has no errors?
It compiled that doesn't have an actual error.
In the compilation?
Yes, ma'am.
So because there's plenty of logic errors that can occur.
There are logic errors we found. The development that we've added to the code given by Tardec was these 3 files. We've added very minor data structures to allow it to read the power of the GVR-Bot itself. And for this code review, we did lightweight code review and used pair programming because myself and Zach Foster completed it. For Mission Commander, we are at version 1.0.0. We have 4 different versions backed up on GitHub and our Gemini. This one's mostly done by myself, and Zach Vosberg is the one who is helping me a lot most. And I have used a lot of testing and implementation help from Cadet 10 because he's better at Python than me, so he's been helping me a lot with that. Next slide, please. So tested, the framework is built for everything, but the clickable buttons don't actually connect to controller yet, so that's where we're at. Errors, ROS topic does not work inside of a Tkinter GUI, which is our big problem right now, that I think Zach Vosper actually fixed last night, so we haven't implemented it yet, but we have an idea how to do it now. Development, we have a controller, pre-planned routes and desk tests, buttons built in, and the controller itself is working for all that aspects. So not even the buttons don't click yet. And again, pair programming and lightly code review.
Which just means that he looks at your stuff and says, yeah, it looks okay?
Right, so the code is done, instead of like, for example, this one is done by over-the-shoulder methods, so Tan's the one in charge of it, and if he needs help, I kind of help him over his shoulder. But when we do the UI and the ROS code, it's pretty much on exactly the same computer, working simultaneously, whereas the over-the-shoulder, we're just kind of watching what he does. We're
But
not really,
that's not, strictly speaking, a review, and you're not evaluating his code. You're just kind of watching.
well, for the evaluation for the CDR, we actually go through and like review the stuff we've written, and we'll critique the aspects we find that are not up to standard, I guess.
The next thing is the data code. The current version is version 1.2.1, and I'm mainly responsible for this code. So we tested the data acquisition through the bus, SQL database login and viewing, and then error handling with the data collection. The main error is the unpredictable frequency of logging. That's why it said approximately 88 hertz, man, because it sometimes slows down whenever the robot does some
Motor.
the motor goes too fast or goes too slow without it changing speed. That's the only thing for the error. Other than that, it works.
Is your data accurately time-stamped?
Yes, ma'am. It's actually timestamped by the second right now. We're trying to look.
But at 84 hertz, that you need millisecond accuracy.
Yes, ma'am. As of right now, for the timestamping, we're getting it from the MySQL database. So we're trying to find other methods of timestamping down to the millisecond.
Okay, because your premise for this whole model is current over time. And if you don't have an accurate timestamp of when you're collecting your data, then then your model, you're inherently introducing error into your model.
One of the things that we're considering doing is connecting a real-time clock to the DATAC. We just, because the DATAC doesn't have its own Linux-based recording software, we haven't been able to implement that yet.
What do you think you actually need in terms of frequency of data collection?
From what we saw from our tests using the multimeter before we had the mobile platform, the distribution of like the fluctuation that we saw was pretty normalized around an average. So we think that we can average across the time. So we're looking at, we were able to do it pretty accurately at 5 hertz. We want to bump it up to see what it's like at the 84 hertz that are possible.
Well, so we go back to signals and systems. We have a Nyquist criteria.
Right.
You want to sample at twice the frequency of the rate at which your data is changing. So
Right.
So with the data logger on the highest frequency setting, you can then figure out what's the actual frequency of your system, your underlying system.
Yes, ma'am, and that's something that we're looking at doing. We only just got it set up to sample this quickly, so we haven't actually tested that yet.
Because you would want to sample above the Nyquist frequency, but there's no value added in sampling at 84 hertz if your Nyquist frequency is 10.
Right. Similar motor controllers that we compared with. I mean, we took a kind of an assumption that it's probably around a 25 amp motor controller, similar to the Sabertooth.
Mm-hmm.
Those operate at around 10 kilohertz, but we don't know for sure if that's what ours works at.
But that's just the frequency at which it's doing its pulse width modulation, or its motor controlling. That the 10 kilohertz of the motor controller isn't the response of the motor itself. And
Right.
that's really what you're modeling, is the motor's response. The motor controller is this box in between the battery and the motor that, at least in theory, is just as your test is, a transmission line that doesn't affect. What you're really trying to characterize is the motor.
I don't think that's totally accurate, man, because the whatever's going through the saber tooth is going to be, it's going to be a transmission, but it's also going to be regulated by the motor controller. So I think that we can measure, by measuring the controller and whatever's pulled off the battery directly, we have no way of measuring the motor or the controller or the computer.
Right,
So
right.
all we can do
Yeah.
is measure from the battery.
Sure.
But the assumption that we're using is that the fluctuations that we see off of the battery are going to be fairly similar to the components that are operating in between. And we haven't been able to
Yeah.
sample high enough yet.
Well, sure, I mean,
to
that's all you can do, and that's all you need. What I'm just saying is that the response of the motor, which is what you're trying to model so that you can then predict current drive in the future, is not gonna be at 10 kilohertz. I mean, you took controls, right?
Mhm.
You know, the motors, whatever it was, the Quanzer motor that you tested in lab 1 of controls, was near 10 kilohertz. It was on the order of hertz.
Right.
And so that's a good thing in your case, because you don't need 80, probably don't need 84 hertz. Because the motor, you know, but what you're trying to, you're essentially discerning those motor constants from the EE or XE472 lab,
Right.
or the 377 lab. So, yeah. I mean, that would be an important value added contribution, you know, just to the scholarly publications for this, because you won't need to, you know, if you can definitively say 6 hertz or 12 hertz or 15 hertz is sufficient, that saves on how much data you've got to collect in your SM bus and the requirements for memory, and everything just propagates from there. Okay.
So just briefly, our GitHub history, this is as of last night. We had 57 commits, and what that consisted of is we have distinct folders for each kind of code, and backed up is each version when something gets changed. Each code in each README describes the changes made, and the errors, or the development happening on. Next slide. Example of our version control is, for example, this was a while ago, but I would add a code or update a version, adding a different code itself, updating a README fixed time. So we're adding code as it's changed, not once the whole thing is finished itself.
Mhm.
So for Michigan, I think there's 4 backup versions. Ross code is 4 or 5. Daytag has a bunch. So 57 commits. You can go back to version 0.1 of everything we have and look at the development from there. Next slide, please.
Our budget so far for the project, we've purchased the 3 Daytex at $150 a piece, and then we've had 3 Raspberry Pis purchased for us, $35 a piece. So our total investment as of right now is only $555. We're being pretty financially.
And then products acquired that we haven't necessarily purchased. The 500 gigabyte hard drive.
A minor thing, just in, that's a gigabyte hard drive,
Should be
capital G and probably a capital B.
Yes, ma'am.
And likewise, on a previous slide, hertz is the unit, and it's also a guy's name, and so the H should be capitalized. Those things, when your autocorrect is often not your friend. Okay, so we're out of time anyway, but the code review was intended to actually show us code. That was the point of the code review, was to show us
We
your
have-
code, not just say we tested it.
We have full code lists.
because the presumption was that you actually identified some modules that you wanted us to look at, and then we would be able to do things like, assess readability, and assess your code design. And without looking at the actual code, I can't assess.
I think what I tried to do was for my model of the mission commander, really the only thing we've designed ourselves that would need some kind of review would be that. Because it does have so many different files and connections and different frameworks, that would be the biggest one, and in there is printed all the different code we have written. So if there were one we wanted help with, would be that. It's right now incomplete because we haven't finished the connection between the controller and the model view. However, that would be pretty much the only thing we would need review the code itself.
Right.
Everything else is pretty simple and short besides that.
Yeah,